This is a walkthrough of problem 3 on practice exam 2 of module 6 in the book Problem Solving Guide for Mechanics and Thermodynamics. We have an 8-gram bullet going 300 meters per second to the right and a 12-gram bullet going 400 meters per second towards it, but at an angle of 20 degrees as shown from the top in the figure below. I don't see any figure. Where's the figure? We need a figure. There's a figure. 8 grams, 300 meters per second to the right. 12 grams, 400 meters per second at an angle of 20 degrees from the horizontal. They collide and melt together due to the thermal energy generated during the collision. Part A, what is the speed and direction of the 20-gram chunk of hot lead just after they collide? How much thermal energy was generated in the collision? So we have a good diagram showing the bullets coming in. Let's label it. We have 8 grams going 300 meters per second to the right and 12 grams going 400 meters per second in this direction. We have two unknowns, the final speed of the bullet glob and the direction in which it's heading, but I like v sub x and v sub y. Those are my two unknowns. The horizontal component of the velocity of the bullet blob and the vertical component of the velocity of the bullet blob. We're going to need two equations. Momentum is conserved in all directions. Let's define the x-axis as horizontal, the y-axis is vertical, and let's write the conservation momentum in the x direction. First, we get the initial momentum in the x direction. That's the 8-gram bullet. It's all x. There's no vertical component, so all 300 meters per second is in the horizontal direction. The 12-gram bullet, we have to multiply the 400 meters per second by cosine 20 to get the horizontal component of the velocity, and we have to stick a negative sign in there to tell the equation that it's a head-on collision. They're not going in the same direction. So we can calculate this by punching out the numbers, and we get the initial momentum in the x direction is minus 1950 gram meters per second, and that's going to be the final momentum of the blob because there's only one mass afterwards. So we can set the final momentum in the x direction to 20 grams times v final x, and we can calculate v final x as minus 97.5 meters per second. As expected, the 12-gram bullet is going to win. It's going to push it back. Now the y direction. Initially, only the 12-gram bullet has momentum in the vertical direction. So we have 12 grams, 400 meters per second, sine 20, we get minus 1640 grams meters per second for the vertical momentum of the 12-gram bullet, and that must be the final momentum of the 20-gram chunk of hot lead because the bullets stick together. So we have 1640 gram meters per second down, 20 grams times v final y. We can calculate v final y, and it's 82.1 meters per second. Let's put these velocity components on the diagram. There's v sub x final and v sub y final of the 20 grams of hot lead. Now we can get the magnitude, which we call its speed, v sub x squared plus v sub y squared, square root, and we get 127 meters per second, and let's put that on the diagram as well. There's the final speed of the bullet. We can get the direction with the tangent function. Let's call that angle theta right here. Tangent theta is minus 82.1 divided by minus 97.5. Let's forget about the negative signs. We know where the angle is. It's right here. So tangent theta is 0.842. So we take the arctangent of both sides, and we get the angle is 40 degrees. So let's stick that on the diagram. That angle is 40 degrees. Now we can answer the problem. It's 127 meters per second, 40 degrees below the horizontal to the left. Right there. Now we can do part B, which should be easier. We just have to calculate the kinetic energies. The initial kinetic energy, substituting in the numbers, converting to kilograms, we get 1320 joules. The final kinetic energy is from this 20-gram blob going at 127 meters per second. 20 grams is 0.02 kilograms, and we can calculate that as 161. So the thermal energy generated was the initial kinetic energy, 1320, minus the final kinetic energy, about 160. So the thermal energy is about 1160 joules. That's it. Good job.